Today's featured speaker is Gregory Valiant is an assistant professor in Stanford's computer science department. Some of his recent projects focus on designing algorithms for accurately inferring information about complex distributions when given surprisingly little data. More broadly, his research interests are in algorithms, learning, applied probability, statistics, and evolution. Prior to joining Stanford, Dr. Valiant was a postdoc at the Microsoft Research Lab in New England, which focused on integrating mathematical and algorithmic sciences with both the social sciences and aspects of the biomedical sciences. He received his PhD from UC Berkeley in computer science and his bachelor's degree in math from Harvard. He currently teaches CS 161, Design and Analysis of Algorithms, this winter quarter at Stanford, which is part of our SCBD portfolio offered to remote industry students. So now I'd like to turn the floor over to Greg.
Okay, well thanks Stephanie, and thanks for logging in. So today I was going to tell you about a few perspectives on how to get a surprising amount of information from a given amount of data. So the sort of mindset that underpins this work is the following question. So if you're given some data that's drawn from a very complex distribution, so what do we mean by complex? Well, maybe it's a very high-dimensional distribution, or maybe it's a distribution with a very large domain or alphabet, so maybe a distribution over rare genetic mutations, or maybe it's a distribution with very complex dependencies, such as natural language. Then, and oftentimes, even if you have a lot of data, the empirical distribution of the data is misleading. In the case of high-dimensional distributions, well, because of the dimensionality, you need an enormous amount of data to kind of fill out the geometry of the space. In the case of distributions over a very large domain, often even when you have lots of data, you still fail to observe some of the domain elements that do arise with non-negligible probabilities. In the case of complex dependencies, well, even when you have lots of data, sometimes you don't actually see all of these complex dependencies. So in these cases, the empirical distribution of the data you have is often misleading. And the basic question is, well, in this undersampled regime, can we still recover accurate information about the underlying distributions? What can you say about the unseen portion of the distribution? Can you say anything about the domain elements that you haven't actually observed? Or, in cases where maybe you can't give great answers to the above two questions, could you still estimate the value of collecting more data? Could you estimate, well, maybe if I were to get 10 times more data or 100 times more data, I would be able to answer these questions? So I wanted to give two motivations for this work. So the first is that even though today's machine learning systems are extremely impressive, currently they still use the data they have extremely inefficiently. So just to give one concrete data point, so humans learn to speak after hearing roughly 50 million words. So between when you're born and when you're 3 or 4 or 5 years old, most people hear 50 million words spoken to them. So again, this isn't distinct words. This is 50 million utterances of words. And so after hearing these 50 million words, most children have a good grasp of grammar, a good grasp of semantics, and they basically speak like humans. In contrast, even the state-of-the-art natural language processing systems today, they are fed the entire Wikipedia corpus over and over and over and over again. And at the end of the day, they still lack some basic grammatical understanding and lack kind of sense of semantics. Okay, so even though today's machine learning systems are very, very impressive, they don't use information that they have all that efficiently. The second motivation I wanted to mention is this apparent paradox that as the number of data sets around us have grown and as the sizes of these data sets have grown, in fact, we're increasingly faced with this problem of seeing these undersampled distributions. And in the next 5 to 10 years, I think we're going to start to see many more advances that are based upon getting more information from the given data set, getting more information from the data that we actually have. So with these motivations in mind, I wanted to discuss 3 sort of different settings that I've been working on recently. And these 3 settings will all have the property that for a given amount of data, even when the empirical distribution of the data is misleading, we'll still be able to accurately say things about the underlying distribution. So in the first part, which is sort of a warm-up, we'll consider a setting where there are lots and lots of people, but each person only has a tiny amount of data. And we'll see that you can leverage the fact that there are lots and lots of people to improve your empirical understanding of each person, even though they only have a little bit of data. In the second part of the talk, we'll consider a setting where we have samples drawn from a distribution over an extremely large domain, and we'll actually be able to accurately infer the structure of the portion of the domain that we haven't seen any samples from. So we'll actually be able to infer things about the number of unseen domain elements that arise with different probabilities. In the last part of the talk, we'll consider a geometric setting. So we're given data drawn from some high-dimensional distribution. And we'll see that even when we have too little data to understand the geometric structure of the distribution, so we'll have too little data to say, oh, these are the big principal components of the distribution, we'll be able to describe what structure is there. So we'll say, oh, we don't know what the principal components are, but we know that there are 5 directions with big variance and 50 directions of medium variance and so on. So while all 3 of these settings are going to be rather different and the results will be different in these settings, there's a common perspective that underlies and enables the algorithms that we'll see in these different settings. Okay, so let's start. So in this first setting, imagine you have n people, and think of n as being very large. And each person has some hidden parameter p sub I. So maybe p sub I is the probability that the ith person gets a flu each year, or maybe p sub I is a probability that each person pays their credit card late each month, or changes jobs, or maybe p sub I is some biological trait. So maybe p sub I is a probability that a person has a male versus a female child, and so on. So imagine we have a data set. So we have lots and lots of people. We have n people. However, each person, we only say, in this case, observe 2 flips of their coin. So we observe 2 independent random variables for each person, which each are yes with probability p sub I and no with probability 1 minus p sub I. So in this case, what can we hope to say about each person's probability? Well, the first thing to observe is that the empirical estimates of the PIs are extremely unreliable. We just have 2 flips of each person's coin. What can we hope to say? So if we look at the first person, they flipped their coin twice, they got 2 yeses. The empirical estimate of this first person's probability is 1. In both tosses, they got yes, empirical estimate is 1. And obviously this is very noisy because we only have 2 flips of a coin. Okay, so in general, if you want to estimate the bias of a coin to error epsilon, you do need to flip it roughly 1 over epsilon squared times. And here we only have 2 tosses. What can we hope to say? Well, suppose we look at all of the data in aggregate and we happen to notice the following phenomena. So suppose we see that actually the number of people who got 2 yeses is roughly equal to the number of people who got 2 no's, which is equal to the number of people who got a no and a yes and a no. And these are all very roughly or very accurately, the number of people with each of these is very close to n over 4. So I claim that based on, if we were to have seen this data, we can actually conclude that almost all of these probabilities, almost all of the p sub i's must be extremely close to a half. So what's the reasoning behind this? Well, suppose that 10% of the people had a probability of 0.6, and 10% had a probability of 0.4, and maybe the rest of the people had probability 0.5. Then I claim that we would actually start to see a noticeable amount of correlation in these 2 flips. We'd actually see more people with the yes, yes, and more people with the no, no, than with the mixed no yeses and yes, no's. So if you think about this a little bit, if we actually saw data like this, I claim that we could really conclude that, at least n minus, n to the 2/3 of these PIs are equal to a half plus or minus maybe 1 over the cube root of n. Okay, so we can make extremely concrete statements about this that really pin down this set of p sub i's. And again, the intuition is that if this wasn't the case, if there was more variation between the PIs, we would have seen very different summary statistics. Okay, so this is pretty amazing. So suppose we saw, we looked at the aggregate statistics and saw almost exactly n over 4 people with each of these outcomes. And based on this, we concluded that almost all of these PIs are very close to a half. And now suppose you said, oh, look at this fourth person. They got 2 no's. What do you think their true probability is? What do you think P sub 4 is? Well, now the argument would be, well, look, almost all of the PIs are a half, so I think P sub 4 is probably very close to a half. And on average, this will be very good. We will get extremely low average error over our estimates of all the people. And this is pretty surprising, right? So if you think about what's going on here, we're estimating P sub 4 more accurately than the empirical distribution based on using information about the independent random variables corresponding to everybody else's coin tosses. So we're estimating P4 not just based upon the tosses of the coin that land heads with probability P4, but also based upon the probabilities of landing heads of all these other independent random variables corresponding to different people. This is pretty surprising. So you might wonder, to what extent is it, to what extent have I cherry-picked a special setting where exactly n over 4 of the people answer yes, yes, no, no, and so on? So it turns out that even in the worst case, no matter what the set of underlying PIs are, you can accurately learn the set of PIs to average error epsilon using only 1 over epsilon samples from each individual. Only 1 over epsilon tosses of each coin, again, as opposed to if you were to naively use the empirical estimate, which would require 1 over epsilon squared tosses of each coin. So this is a very simple setting. We're just trying to estimate the set of biases of coins. It rises in many settings, very useful, but there are lots of more higher level analogs of the setting which are worth considering and which we are thinking about now. So there are these more complex distributions, so instead of just each person having 1 coin, imagine each person has something that happens with probability P sub I, something else that might happen with probability Q sub I, and so on. Right? So maybe each person corresponds to a visitor to a website. P sub I is whether they buy an item. Q sub I is whether they end up asking for something on the help page, and so on. So maybe there are these more complicated distributions. To what extent can one get analogous results for these? You might also wonder how you can leverage additional structure to the problem to be able to do even better. So these are some avenues that we're currently thinking about. So just to summarize the punchlines from this first part of the talk, so even with very little data from each person, we can accurately recover the set or population of distributions by leveraging the fact that we have data from lots of people. And as we saw, so in many cases we can then use this information to go back and improve our estimates of individual people's distributions. Okay, so this was the example where first we concluded that almost all of the P sub i's must be very close to a half, and then we go back and say, well, the fourth person, even though the empirical estimate looks like their probability is 0, their P sub I is also probably a half. And you can view this as a special case of what's known as Stein's phenomena. So this is named after the late Charles Stein, who is a statistician at Stanford and passed away a couple months ago. And he was the first one who noticed that you can actually improve estimates of some parameters based on observing independent random variables. So even though I'm trying to estimate the fourth person's probability, I can improve my estimate of this on average if I look at these other independent random variables. So now we'll transition into the second part, where we'll talk about how to accurately estimate properties of the unseen portion of a distribution. So before I go on, let me stress that all of the techniques I'm talking about are ways of cleaning up the empirical distribution of the samples, and these are ways of cleaning up the empirical distribution without making any prior assumptions on the distribution in question. So we are doing this based purely on an understanding of how the randomness from the sampling process ends up, in some sense, noising up the empirical distribution of what we see. Okay, so in this second portion, we'll be talking about a setting where we're given independent draws from some distribution over a discrete support. So think about it as we're sampling species of fish from some population. So we're independently drawing fish from an ocean And we should think about this as we're sampling each fish with probability proportional to the probability of that fish in the ocean. Okay? So in this example, we drew 6 fish, and we saw 3 different species. What can we hope to say about the underlying distribution of fish? Well, the empirical distribution of the sample, this is the maximum likelihood distribution. It maximizes likelihood of having drawn exactly what we observed. However, it does not capture the unobserved portion of the distribution. So in this case, we saw 3 different species of fish. Maybe there's a 4th species or a 5th species of fish in the ocean. The empirical distribution does not account for this at all. So there are a few natural questions. So one is, what could we even hope to infer about the unobserved portion of the distribution? Can we hope to say anything about it? As we'll see, the answer is yes. We can actually say very nuanced things about this. And the second point is, well, how can these inferences about unobserved portion of the distribution yield better estimates for aspects of the distribution that we care about? Suppose you want to estimate the entropy of the distribution or other properties of it. How can we leverage a better understanding of the unobserved portion to improve these estimates over just the empirical estimate? So in some sense, the motivation for my work, or the inspiration for my work on these problems, goes back to very early work of R.A. Fisher and Alan Turing, who are respectively the sort of godfathers of modern statistics and computer science. So in the case of Fisher, he was given this data of a biologist named Courbet. So Courbet spent a year in the Malaysian jungle in the 1940s collecting butterflies. And this plot at the bottom of the page, this is Courbet's butterfly data. So what does this represent? Well, the leftmost spike represents the fact that while he was in Malaysia, he discovered, or he caught 110 species of butterfly. And of these 110 species of butterfly, he only ever saw individuals from them exactly once. The second spike represents the fact that there were 75 species of butterfly that he caught exactly twice. The third spike represents the fact that there were something like 45 species of butterfly that he caught 3 times in his year in Malaysia. And way off on the right of the plot, which is cut off, yes, there's the common brown moth, and he probably caught that 1,000 times, and that corresponds to a spike of height 1, representing the fact that there's 1 species that he saw 1,000 times. So this will be a spike at location 1,000 of height 1. So while he was there, he discovered something like 230 species of butterfly. And he sent his data to R.A. Fisher, who is the big statistician of the time. And he said, listen, I'm thinking about staying for another year in the jungle. Can you tell me how many new species you think I would discover if I catch butterflies at the same rate as I did during my first year? And it actually turns out that there's an extremely accurate estimate for this. So if you compute this alternating sum, so take the total number of species you've seen exactly once, subtract the number of species you've observed twice, add the number of species you've seen 3 times, subtract the number you've seen 4 times, compute this alternating sum, and this gives an essentially unbiased estimate of the total number of new species you would expect to discover in the same time period if you're collecting butterflies at the same rate. And again, this assumes nothing other than the fact that you're collecting butterflies at the same rate and that the underlying distribution of butterflies is fixed. So this is pretty surprising, right? We're accurately saying something about the unobserved portion of the distribution. So at roughly the same time, so Alan Turing and I.J. Good were working at Bletchley Park on the British World War II effort, and they were interested in estimating a similar thing. So they wanted to estimate what's the probability that the next German Enigma machine ciphertext is a new ciphertext that we haven't seen. Phrased differently, in Courbet's language, this is estimating the probability that the next butterfly that he catches is a new species that he hasn't seen. A third way of stating this is you're trying to estimate the total probability mass in the true distribution that consists of domain elements that you haven't observed yet. Okay, so this is the missing mass, in other words, the mass in the true distribution which is missing completely from the empirical distribution. And it turns out that there's a very simple estimate for this, an essentially unbiased estimate for this missing mass. And this is now known as the good turn frequency estimation scheme. And it says, look at the total number of domain elements that you've seen exactly once, divided by your sample size, and this tells you the probability, a good estimate for the probability that the next domain element you see is new. So if you think about this, what does this mean? Well, this means if you want to know what's the probability that the next song you hear on the radio is a new song you've never heard before, well, think back, count the total number of songs you've heard exactly once in your life, divide that by the number of songs you've heard in total, and this gives you an estimate for the probability you'll be surprised with the next song you hear. Okay, and this makes sense. If in general you're surprised by 3% of the songs you hear, the probability you're going to be surprised by the next song you hear is probably 3%. Okay, so Turing and Fisher give extremely accurate estimates in some sense of a single parameter of the unseen portion of the distribution. So how much more can we hope to understand? So in our results, we're actually going to be able to recover estimates of the structure of the unseen portion, not just estimates of the total amount of mass, but actually estimates of the number of unseen elements that arise with different probabilities. So what is this good for? Well, one can answer questions of the following form. So one can ask questions like, well, what's the value of collecting more data? If we were to collect 100 times more data, how many more domain elements are we likely to observe? Or we could ask questions like, how much data is necessary before we actually are likely to see 99.9% of the phenomena that arise in a given distribution? So this latter question might be relevant for settings like autonomous vehicles, where you want to know how much more do we need to drive these things until we actually have a good coverage over the sort of events that arise when you're driving. And there are a number of more scientific reasons why you might care about understanding the structure of the unseen portion, including understanding properties of the unseen rare mutations in humans, and I'll give some concrete examples of that towards the end of this portion. Okay, so how can we do this? Well, let's begin with just a thought experiment. Suppose we actually take 100 million samples, we draw 100 million independent draws from some distribution, and suppose we see about 1 million domain elements, and each domain element we see roughly 100 times. And if you were to look at a histogram of the frequencies, suppose we see something like this. So again, what does this plot represent? Well, the big spike at 100 represents the fact that there are lots and lots of domain elements that we see roughly 100 times, or see exactly 100 times. And yes, there are some domain elements that we only see 80 times or 90 times, and some domain elements that we see 120 or 130 times. Okay. So you can think of this as a histogram of the data. So this is a histogram of the frequencies. And suppose someone asked you, well, what distribution do you think these samples were drawn from? In other words, if someone said, hey, look at this one domain element, we observed it 130 times. What do you think its true probability is? Would you answer, well, the empirical probability is 130 divided by the sample size, so 130 divided by 100 million? Or would you do something else? So I claim that actually, based on no prior assumptions on the distribution, only an understanding of the mapping from a true distribution to an empirical distribution, we can accurately denoise this distribution, denoise this empirical distribution, and conclude that the true distribution from which these samples were drawn is probably extremely close to a uniform distribution over 1 million domain elements. So why is this the case? Well, suppose the true distribution actually were a uniform distribution over 1 million domain elements. If we had drawn 100 million samples from this, we would have seen something extremely similar to this picture. Most things we'd see roughly 100 times, some things we'd see more, some things we'd see less, and the standard deviation and the number of times we see different elements would be roughly 10, and it would roughly look like this picture. If the true distribution had any significant variance in the probabilities, then after you take into account the extra sampling noise that's added just from the sampling process, I claim we would end up seeing this histogram that's even fatter, that has even more variance. One way of thinking about this is that the mapping from the true distribution to the empirical distribution can be almost thought of as a sort of convolution operator, something that kind of adds noise and smears out the probabilities. And the question is just to what extent can you deconvolve, can you denoise, can you remove the effect of this sampling noise? And in this case, I claim you can do it very robustly and very accurately. And what does this mean? Well, this means that if someone comes and says, hey, this element was observed 130 times, what do you think its true probability is? You can safely say, well, yes, I know this guy was observed 130 times, and this other domain element was only observed 80 times, but I think that actually the true probabilities of them are probably almost the same and probably equal to just 1 over a million, just like almost all these other elements. Okay. So this is an analog of the reasoning that we did in the first part. Okay, so we can do some denoising. And one question is, well, how far can we push this? So let's just continue trying to do this kind of mental experiment. So suppose we have a histogram based on k samples, and we see something like this. Well, we'd say this looks like maybe it corresponds to a uniform distribution over k over 100 elements. This is what we just did. Why? Because if the true distribution had any significant variance in the probabilities, we would expect to see something slightly different from what we see. Of course, proving that might be difficult, but that's the reasoning. Okay, let's look at another example. Suppose this is actually a histogram based on 10,000 samples drawn from some distribution. What distribution do you think this was drawn from? Well, you might recognize that this kind of looks like a Poisson distribution of expectation 5. So you could argue that, well, seeing this is consistent with having drawn these 10,000 samples from a uniform distribution over 2,000 elements. And in this case, you'd be right. So this histogram was made by me sampling 10,000 things in MATLAB from a uniform distribution over 2,000 elements. How far can we push this? Well, you might recognize that this is a Poisson distribution of expectation 2 and think that maybe this corresponds to a uniform distribution over support size 10,000 divided by 2 over support size 5,000. And you would be correct. Maybe this corresponds to a uniform distribution over 10,000 elements. Maybe this is a uniform distribution over 20,000 elements. Maybe this is a uniform distribution over 50,000 elements. So how far can we push this? So at this point, what we're claiming is actually pretty impressive. So we have a histogram, we have data based on 10,000 samples. We've only seen 9,000 distinct domain elements. And yet we're claiming we can reason that this data was probably drawn from some distribution supported on 50,000 domain elements, and that this distribution is probably extremely close to uniform. So we haven't seen most of these domain elements, yet we're actually claiming that we can accurately describe roughly how many of them they are and roughly their true probability. So the natural question is, well, how general is this? How general and how far can this reasoning be pushed? So in all of these examples, we were thinking about uniform distributions. And the only reason we were thinking about uniform distributions is because it's easier to do our mental calculations on them. So what can we say about non-uniform distributions, and how can we actually make this approach rigorous and turn this into an actual algorithm? So if you think about what we were doing, we were basically asking what distribution has an expected histogram similar to the observed histogram of the samples. And it turns out that you can write this problem, you can write this problem that we were solving in our heads on the previous slide as a linear program. So I won't explain exactly what this linear program is, but basically just asks, find me a distribution whose expected histogram is close to the observed one. Why does it end up being a linear program? Well, because we only care about expectations and linearity of expectation. That's where it comes from, but I won't go into details. So what does the algorithm do? Well, it finds one of these distributions via linear programming, and this linear program basically just defines a feasible region of distributions which are all consistent with the observations. Of course, the technical challenge is then to argue about how the diameter of this feasible region shrinks as our sample size grows. So we have some concrete technical results regarding this, which are actually, they're tight to constant factor. And I just wanted to give you a flavor of what these sorts of things say. So given n independent draws from some unknown distribution, we can recover the set of probabilities, p sub I, as well as an empirical distribution would, if the empirical distribution would have been based on an extra logarithmic factor more samples. So 2 points. So the first is we're only recovering the set of probabilities p sub I. We're not recovering the underlying domain. So think of it this way. So suppose you go fishing, you catch lots of fish. We're going to recover a set of probabilities of the species. Although if you haven't caught any tuna, I'm not going to say, oh, there must be a tuna in the ocean. Okay, so I'm not going to label the domain. I'm just going to try to recover the set of probabilities. So one corollary of this result, which is maybe easier to understand and easier to parse, is if you're given n independent draws from some distribution, you can accurately estimate the number of new elements that you would see in a larger sample, and you can do this for samples of size up to order n log n in the worst case. So in most practical settings, we seem to be able to accurately infer the number of new things we'll see from much, much larger samples. But this is the best we can do in a worst case sense, and there's a matching lower information theoretic lower bound. So I wanted to give a quick practical application of this. So this is in joint work with James Zhu, and this appeared in Nature Communications. So currently we have 60,000 genomes of healthy individuals that have been sequenced. So one natural question is, what's the value in sequencing larger cohorts? So say we sequence 500,000 people, 2 million people, 10 million people. What's the value in this? How many more new medically relevant mutations are we likely to see if we sequence more people? So applying the linear programming-based algorithm from the 2 slides ago, we can do the following sort of validation. So yes, we have 60,000 genomes of healthy individuals. Suppose we only looked at 6,000 of them. And based on those 6,000, we try to estimate how many new mutations of a certain medically relevant type we would be likely to see if we actually had 60,000 genomes. So based on the first 6,000 genomes, we can predict how many new things we would have seen given more genomes. And the blue line is our predictions. The red line is the ground truth, because we do actually have 60,000 genomes. And then the light blue area corresponds to one standard deviation over different choices of the 6,000 size cohort out of the 60,000 genomes. So we're doing quite well. So then the fun part is to say, well, we do actually have 60,000 genomes. You know, what would we be likely to see if we sequenced 250,000 or 500,000 more people? So just to provide a tiny bit of background on this. So here we are looking at loss of function mutations. So a loss of function mutation is a mutation which will break that given gene. So on average, most healthy people have maybe 1 or 1.5 loss of function mutations, and it's not a big deal. So one thing people are doing at the Stanford Hospital now, if you come in and you're very sick, it's usually children who have very strange symptoms, and it's not clear what's wrong with them. The people at the hospital start by just sequencing their genome and looking for loss of function mutations. So they ask, you know, are there any mutations which we know break a given patient, that break a given gene in this patient? And then what do? For each of these broken genes, they ask, in this cohort of 60,000 healthy individuals, were there any healthy individuals who also had this broken gene? And if the answer is yes, there are lots of healthy people who also have this broken gene, then they say, well, this broken gene probably isn't causing the sickness. If none of the healthy people have this broken gene, then they say, oh, maybe this broken gene is what's causing the sickness. And then, you know, they try to figure out, what does this gene do? Maybe it codes for some protein. Maybe you can synthesize this protein and inject it into the patient, and then the patient gets better. Of course, we have 20,000 genes. We only have 60,000 healthy people's genomes, so there are lots of genes which might be okay to break that we haven't observed. And this plot basically tells us how many more individuals would we need to sequence in order to get a pretty good coverage over the genes for which it's okay to have broken in a healthy person. So this is a real valued setting, and we're going to be trying to estimate a covariance matrix, and this is joint work with Wei-Hao Kong. So suppose we're given n independent draws from some d-dimensional distribution. A natural question is to understand how large must n be, what must our sample size be, in order to understand the structure of the distribution. And one question is, well, if we have too little data to actually find the structure, so maybe we're not going to be given enough information to accurately return top principal components or eigenvectors of our distribution, can we still say whether or not there is structure in the distribution? So could you say something like, listen, I don't have enough distribution to tell, sorry, I don't have enough data to tell you which low-dimensional space your distribution lies in, though I do know that it lies in some low-dimensional space. Okay, so this is kind of a thought experiment. Suppose I have my data consisting of 1,000 independent draws from some 1,000-dimensional Gaussian distribution. And the Gaussian distribution has mean 0, and I'm not sure what the covariance is. And if you were to look at a histogram of the eigenvalues of the empirical covariance of the data, so again, you have 1,000 data points, you just look at the covariance of this data, and you look and you ask how many directions are there that look like there are lots of variance. And you plot this histogram. Suppose this is what you see. So what does this mean? This means that, well, there are lots of directions that have almost no variance. That's the big spike at the left. And there are a few directions that have variance, 4 and 3 and so on. Okay, so you have your data. It looks like there are lots of directions. It looks like there are 200 directions with very little variance, a couple of directions with big variance. And now suppose someone asks you, what was the true covariance structure of this underlying distribution? Well, I claim that in this case, the empirical eigenvalues are very misleading. And in fact, this data was generated by taking 1,000 samples from an identity covariance Gaussian. So this means that all of the directions have the same variance. However, because we only had 1,000 samples from our 1,000-dimensional distribution, just due to the randomness, it looks like there are some directions with big variance and some directions with small variance. If you were to run this experiment again, if you were to take another 1,000 samples from the same Gaussian and plot the eigenvalues of the empirical covariance, you would get this exact same plot again. And if I kept doing this, you would keep getting a plot very similar to this. So now suppose a year later, some doctor came up to you and said, hey, I got this new data. I'm looking at the covariance structure in rare mutations or some medically important something or other. And this is my covariance structure. Look, there are a bunch of interesting relationships that have this big variance. What would you say? You would say, oh, I remember this plot. I know this curve. This curve actually is the curve that arises when you have no structure, there are no interesting relationships in the data, you just have too small of a sample size. Okay, so I claim that every time you see a plot of this, a plot that looks like this, reflecting the eigenvalues of an empirical covariance matrix, you can safely conclude that actually there's no structure in the underlying distribution. Okay, so one question is, well, suppose you actually do look at this histogram of eigenvalues of an empirical covariance, and it looks something different than this. To what extent can you then denoise it and reveal the true covariance structure of the distribution? And well, you can apply the same mindset as we did earlier, but using very different techniques to say things about this. So maybe I'll skip the formal skip the formal statement. So just to conclude with a few final thoughts. So we discussed 2 and maybe 3 different settings. And in all 3 of these settings, the underlying approach was the following. We first understood the mapping from the underlying distribution to the empirical distribution. And then the kind of crux of what we were actually doing was to try to invert this mapping. So to say, suppose we actually saw this empirical distribution, what does this tell us about the true distribution underlying it? So we're inverting this kind of mapping from the truth to the empirical. And in these 3 different settings, it yielded, in some sense, pretty surprising results that actually lead to meaningful algorithms. Okay, so if you get nothing else from this talk, I hope you at least remember that, well, in many settings, even when the empirical distribution is misleading, you can still often extract surprisingly accurate information. And the second point, that there are many extremely basic settings that you would have thought statisticians maybe might have understood a century ago that we still don't understand. Okay, so there's much room for future research kind of at this intersection of algorithms and statistics and information theory and learning. So thank you. So I guess now maybe we'll open it up for questions. So I guess there are a few questions I wanted to address. So there was one question from Andre Koch who asked, how do you know that the unseen distribution law is uniform? So this corresponds to the second portion of the talk. This was where we did this thought experiment starting with, suppose you had 100 million samples and you happen to have seen roughly 1 million domain elements, each observed roughly 100 times. So in this kind of thought experiment, it did turn out that the unseen distribution law was uniform. So all of these were actually uniform distributions. And so the question is, how do we know this? And well, the claim is, if you were to have seen data that actually looked like this data that I was hypothetically giving, you can actually robustly conclude that the true underlying distribution is uniform. The results apply much more generally. So even if the true underlying distribution isn't uniform, this linear programming approach to inferring the underlying structure will actually accurately tell you the structure, even if the underlying distribution is not uniform. The point of these examples was more just to give a concrete example that's somehow simple enough that we can actually think about it. But the underlying techniques work much more generally. And this is actually, I guess, a similar response applies to some of the earlier questions about the kind of warm-up, the first part of the talk, which asked, are we assuming that the individuals are all identical and independent? And the answer is, well, we're assuming they're independent but not identical. So maybe some of the people have larger probabilities, some of them have smaller probabilities, and we would actually be able to infer the underlying set of these probabilities even if they're not all the same. And when I say we can infer the set of probabilities, again, to start with, we're not trying to figure out each person's probability. So I don't want to know, if someone just tosses their coin twice, I maybe will never really know what their true probability is, but I'll infer roughly how many people have probability 0.4, how many people have probability roughly 0.5, how many people have probability roughly 0.6. Okay, so I guess one other question that's actually a really, really nice question from Jan Golkowski. So they asked, well, what, if any, is the relationship between these techniques and deconvolution approaches such as used in signal processing? So this is a very good question. So in the, if you think about what the mapping is between kind of a true distribution and the empirical distribution, in many cases, this does look like you're convolving the true structure of the distribution by some noise operator to yield the empirical distribution. So for example, if we have a uniform distribution over 1 million elements, and then we take 100 million samples from this, the empirical frequencies will kind of look like we convolve this big spike of uniform distribution by some sort of Gaussian type distribution. And in that sense, you can almost view these techniques as deconvolving to remove the effect of sampling, basically. From a technical perspective, this is actually a little different. So usually when you think of convolution and deconvolution, you have a fixed kernel. In this case, the mapping from the true distribution to the empirical distribution, it's not actually a convolution. Even though it's some sort of blurring operator, it's kind of a much more complicated blurring operator, which makes it, in general, harder to deconvolve. So particularly in the last setting that I discussed, where you have some distribution of empirical eigenvalues of a covariance matrix, it's kind of very clear that the mapping from the true structure of the geometric distribution, the true eigenvalues of the covariance, to the empirical thing, it's not just a convolution. It's some very strange kind of noise operator that behaves very differently for the big eigenvectors and the small ones. And so that's where kind of the technical difficulty comes in. That intuitively, you want to do this denoising deconvolution, but it's not actually a clean deconvolution. Okay, so one of the questions asked, do I have an example of eigenvalue distribution for covariance matrix with meaningful structure? So I do have some plots I can show. So each of these plots corresponds to the, you could think of this as the cumulative distribution function of the eigenvalues of a distribution. So what does this actually mean? So the blue line is the true, corresponding to true distribution. And this means that, well, half of the eigenvalues are 1 of the covariance, and half of them are 2. What does this mean? This means that we have some high-dimensional distribution, and half of the directions to variance 1, half of the directions to variance 2. If you were to look at the empirical covariance matrix, the very light blue lines that look like these curves, this represents the eigenvalues of the empirical covariance matrix. So in particular, if you have relatively few samples, the directions of variance 1, the directions of variance 2, all just get blurred together, and it looks like, oh, some directions to variance 1.5, some directions to variance 0.3, and so on. Using this sort of, I guess you can almost think of it as a deconvolution approach, even when the number of samples is linear or slightly smaller than the dimension, we can actually recover the underlying structure, namely that there are half the dimensions have variance 1 and half the dimensions have variance 2. And we have other examples of cases like this where there is actually structure in the underlying covariance matrix.
So maybe, Greg, now that we're at the top of the hour, you can take one more question.
Okay, so yeah, I'll start. I guess I'll finish with a slightly more kind of general question. So this question is from Orlando Tucker, who asked, how important is this information in machine learning and deep learning? So this is a good question. So most of the work I do kind of focuses on kind of fundamental kind of questions that are kind of more of a theoretical nature. And I guess my answer is twofold. So looking forward, at some point I do think if we want progress in machine learning and deep learning to continue at the rate that it has, we will actually need to start thinking about how do you get more information from the data than currently. So deep learning has done a lot of great things, but it's extremely data hungry. So you really do need to give it a lot of data. And if you think about it, what's the chance that we're going to get an extra factor of 1,000 or 10,000 more good text data? Not great. We already have all of Wikipedia. Finding an extra factor of 10,000 more good data. It doesn't seem like we should go down that path. Instead, it seems like we should try to figure out how do we get more from the data we have. I guess from a very concrete standpoint, so one can plug in some of these techniques kind of below the deep learning or more high-level machine learning portions of a system. So one can use these sorts of techniques to somehow correct empirical distributions a little bit and then hand them off to these higher-level systems. And also, I guess, wanted to mention that, there's a lot of kind of higher-level machine learning stuff, but there's also a need to actually concretely, get information about the value of collecting more data and questions like this. So one thing I'm starting to think about is how do you use these ideas together with, higher-level machine learning things to ask, if you were to take 10 times more data, how would the performance of your systems improve and this sort of thing. So at least some of the ideas can work nicely in conjunction with these machine learning and deep learning approaches. Okay, so thank you.
Great. So thank you, Greg, for a wonderful presentation and for taking time to answer some of our attendee questions. And we want to thank you for taking the time to attend today, and hopefully we'll see you at our next webinar. Have a great day.